In this next slide, we are going to talk about what's temperature, what is heat, and how we are differentiating them. So temperature is actually a property of an object, just like pressure, volume, amount of object. For example, for gas, it could be number of moles. So just like that, it's a property of an object, and it's basically a measure of kinetic energy of gas. Because gas particles are constantly in motion, this temperature reflects that random motions of particles. We will talk more about this, like how gas moves and what kind of metrics do we have in order to quantify this motion of gas particles. But for now, we just learn temperature as a property that reflects these random motions of gas particles. On the other hand, heat involves the transfer of energy between two objects due to temperature difference. We have a hot body and cold body. That's how we refer to objects in terms of temperature difference in thermodynamics. And when they are in close contact, when two objects that are having different temperatures are brought into contact, there is some energy transfer occurs between those two objects, and we say that energy is dissipated through heat. So if you remember from our first slide, energy is the system's capacity to do work or produce heat. So heat is just some form of energy transfer that stems from the difference in the temperature. It's definitely not a property. We often talk of heat as if it's a property of an object, like heat of an object, but there is not a such thing. It's just a process. Heat is not a property, but a process. Energy transfer process that results from temperature difference. If we want to talk more about this process of heat, because we define this temperature as a property that reflects the random motions of particles. So when you increase the temperature, you are actually increasing average kinetic energy, and average velocity of gas particles also increased. So higher temperature means that gas has a greater average kinetic energy, which gives rise to higher average velocity of the gas particles. So in this picture, you can see particles at different temperatures, but that they are just in adjacent chambers. So here, longer tails means they have higher velocity. So just by looking at this picture, we can see that this is chamber on the left is actually contains particles that have higher temperature than the ones on the right hand side. And in this thermodynamics context, we refer to them as hot body. What's going to happen here is that gas particles in the left-hand side of the container are at higher temperature, and thus they move at a greater average velocity than the particles in the right side. All right? So when the particle in the left side, the hot body, collides with the membrane at the same time and on the exact opposite side as the particle on the right side. So imagine that they collide to the same point. What's going to happen is that energy is going to be transferred from faster moving particle on the left side to the slower moving particle on the right side that has lower initial velocity. So as this process continues, average kinetic energy on the left side will decrease and average kinetic energy on the right side will increase. Eventually, average kinetic energy on each side will be equal, and the temperature of the gas samples will also be same, will be equal to each other. And when this happens, the particles will still be on motion. Please don't think that if this process ends, the energy transfer stops, temperature becomes same, and then they stops. No, gas particles are always in constant motion, constant random motion. But when the process stops, energy transfer process stops, they will be moving with the same average velocity because they still will have some certain amount of temperature. That means they will still have certain amount of kinetic energy, which means they will have certain motion that is represented by some value of velocity. We used gas here in order to visualize this process, this energy transfer and the difference between temperature and heat and a relation of these to the kinetic energy and the velocity in terms of gas particles. But the similar process occurs with solids and liquids because atoms and molecules, it doesn't really matter what aggregate state they are in, atoms and molecules are always in constant motion. Even that motion is merely vibrating, such as in solid. So in that sense, temperature is a measure of average kinetic energy of particles in solids and liquids as well as in gases. So for any hot body that's in thermal contact with cold body, energy is transferred, and that energy transfer is called heat. We are moving to the next slide. And in this slide, we are going to define what is state function. But in order to understand that, we need to define energy transfer dynamics. We have total energy. When I'm saying total energy, I'm saying the total energy of the universe, system plus surroundings. And here we have to define what we mean by system and surrounding. System is a part of universe on which we are focusing our attention. It could be reaction vessel, it could be reaction glass where we conduct this process, this reaction. And surroundings include everything else in the universe outside that system. Okay, so when we are saying total energy, we're talking about the energy of system plus surroundings, basically energy of universe, and that's constant regardless of the pathway. So we have to define pathway as well. There's a work that is energy used to move object, a motion against opposing force or force acting on over a distance. So these are definitions of work. There's also heat, that's energy dissipated through friction or temperature difference. So basically some kind of energy transfer. And there's also pathway that determines distribution of energy transfer. Is it work, is it heat, or is it combination of heat and work? Because we have some state A, it goes to state B, let's say from initial conditions to final conditions, and energy of the system is changing, right? And the question is how energy is transferred. Is it transferred through heat, or is it transferred through work, or is it maybe combination of both? So in our previous example, when two objects collided each other, object A and B, and then B moved up, right? And you see there was a potential energy for A, and then it's converted to what? It's converted to potential energy of B through work. There was some work that's done by the object A on object B, but there was also frictional heating, right? So there was a heat, there was a friction, and some energy that's stored in A, which we refer to as potential energy of A, is also converted to some heat, which in turn is used in order to slightly increase the energy of the surface of the hill. So in that case, we say that we go from point A and point A, let's say point 0. We go from point 0, which represents A on the top and B on the bottom, and we go to the point 1, point 0 to point 1, and that point 1 represents B on the top and A on the bottom. Yeah, and now you have a difference in energy transfer occurred, and some of them went to the potential energy of B and also some heat. And based on this dynamics, how this energy transfer occurs, we actually define a state function. The state function refers to a property of the system that depends only on its present state, okay? And when we say present state, we are talking about the current condition of the system, the current properties, that current temperature, current pressure, volume, whatever properties, collection of properties, they define the present state. When I say state function, it could be energy, it could be heat or work. State function depends only on its present state, and it does not depend on the path taken. So we have a pathway, right? Point 0 goes to point 1. Energy of the system is changing here, and it could be dissipated through heat, or there could be some work that's done on the system, or there could be a work that system does. So regardless of this pathway, the total energy is going to be constant, but the energy of the system could increase or decrease, which would be compensated by the opposite change in surroundings, obviously. But we are defining some functions. For example, energy. Energy is a state function because in order to find the difference in energy between 2 points, we just need to subtract the energy of the system at point A from the energy of the system at point B. And that's going to give us energy difference. And it doesn't really matter how you got to the point B from point A. But work and heat are not state function. Work and heat, they depend on the pathway that's taken. We will talk more about these later when we talk about pathway, because right now it's a bit ambiguous to talk about going from point 1 to point 2 because we haven't talked about what kind of pathways we can take actually in order to arrive at the final state. So when we learn more about these, you will once more confirm that energy is a state function and work and heat are not state function. And as we go through, as we learn more functions like entropy, enthalpy, Gibbs free energy, we will also be able to categorize them, whether they are state function or not. There's going to be energy zero for state zero, and there's going to be energy final for state final. And the difference between the energy is just going to be the same, no matter what kind of path you took in order to go from state zero to state final.